Okay. A few more people might trickle in, but I'm going to go ahead and start us off. So we have leave plenty of time for questions at the end. Good afternoon, everyone. Thank you for attending today's webinar on all things residential insulation. This webinar will be recorded and the recording is posted to the Code Adoption Toolkit in about a week or two. Give us a little time to do that. But if there are any issues with audio, feel free to write me in the chat. And my name is Erica DeLello. I'm a project manager for Noresco. This series is sponsored by Colorado Energy Office with the training materials created by BuildTank. So Robbie and I have been working with the Colorado Energy Office to provide trainings just like this one. This is a continuation of our Wednesday webinar series. There are others on the list. If you registered for this training, you're also registered for the others in the series. And we've got vapor management on the docket, passive house, mechanical ventilation controls, and then IECC 2024 when that hopefully gets released in the next month or so. So definitely attend those as well. And I do want to mention that we also have the offering of technical assistance for jurisdictions. So if you're looking at adopting the 2021 or any REACH code amendments, anything along those lines, we're here to help. It's a no cost to you service where we can help your jurisdiction update to the latest building codes and provide a whole bunch of different opportunities for you guys in order to have us, say, attend a city council meeting or review some of your code language or write up some amendments or anything along those lines. So I want to call out, of course, the Code Adoption Toolkit. You know, there's a whole bunch of different resources on it, including all the previous recordings for these trainings. Today, I want to highlight, the Colorado Codes helpline. And the helpline's available to anyone on any of the REACH codes or any REACH code or any of the I codes as well. So for example, if you're a jurisdiction and you need assistance on a plan review or homeowner or an engineer that has a question about code and how it applies, you can submit a ticket and a subject matter expert will get back to you in just a few days' time. And so you can access the code helpline through this link, or it's also actually linked in the Energy Code Adoption Toolkit as well. So go ahead and stop sharing my screen. You know, throughout the webinar, we want to encourage questions. So please use that Q&A function, and I'll let Robbie know at the end of the presentation. This gives us, you know, the opportunity to make sure we get through everything before we address questions. There's also the ability to raise your hand and ask a question, and then I can unmute you. And then lastly, there will be a survey window that pops up. Please take a minute to provide feedback so we can continue to improve on these webinars, and it also helps us to determine what topics you guys want to hear about. So with that, today's presenter is Robbie Schwartz, and Robbie founded BuildTank Inc. to be a practical building think tank to do research, education, and work with builders to ensure that their homes not only comply with the codes and programs, but also perform. At BuildTank, they strive to use what they learn from their field work to affect meaningful change in the construction industry. Robbie's also the new homes building advisor for Boulder County's Marshall Fire. And so I'm going to pass it over to Robbie, but before I do that, I do see one raised hand. Megan, I'm not sure if you meant to raise your hand, but I'm going to go ahead and allow you to talk. If you have a quick question before we begin, go ahead and unmute yourself. Okay, I'm not hearing anything from you, Megan, so I'm going to go ahead and remove that permission to talk. But if you do have a question, feel free to write me in the chat and I'll get back to you as soon as I can. Okay, go ahead, Robbie.
Great. Well, thank you everyone for joining us today on this presentation of all things residential insulation in the IECC. I'm actually going to turn my video off as well so you can concentrate on the slides, and then we'll come back on at the end here. Today, we're going to be talking about insulation, obviously, but we need to first discuss the building thermal envelope. We'll talk about thermal flow, how insulation works. IECC R values and U factor requirements, those tables that are in the IECC itself. Assessment of insulation, installation, some installation requirements. We're not going to obviously have time to go over all of them, but and then ultimately we're going to be talking about why is the IECC wanting us to move insulation outbound, outside of the cavities to the exterior of our buildings. So to begin with, we have to have a pretty clear understanding of the building thermal envelope. And as defined by the IECC, it's talking about an assembly of things for two reasons. One, it's not just the basement walls or exterior floors or all those different components. It's what's inside those components or what those components do. They create a clear and defined boundary between conditioned space and exempt unconditioned space. And that's why the code also asks us to depict the building thermal envelope on our construction documents so that everybody has a clear understanding of what is conditioned space and what is unconditioned space. And then ultimately, what creates that boundary condition? It is those components, but it's more than just those components that create the boundary condition between conditioned space and unconditioned space. It is the continuity of our thermal control layer in the house, which is that insulated portion of the house, in alignment with the air barrier or air control layer of the house. You need both of those things to be able to create that building thermal envelope. So when we talk about an assembly of things, we're really talking about a belts and suspenders approach where we have a primary interior air barrier, which would be the continuity of our drywall system, and a primary exterior air barrier, which would be the continuity of our exterior sheathing in it. And then in between those two things, we have the continuity of our thermal barrier in there. So, and then when we don't have the continuity, the code is specifically asking us to add supplemental air barriers. And they're doing that as examples of spaces. So really, we have to have continuity all over the place, but then the code might say, well, look at this location, this assembly more carefully, because that's an area where we often don't have that continuity, like the air barrier behind a tub on an insulated wall, or the air barrier on the exterior side of an attic knee wall that's adjacent to a ventilated attic. Those are areas that are called out specifically for supplemental air barriers because the continuity is often broken in those locations, but we're also looking at ensuring that we have the totality of our building thermal envelope assembly and the kind of the belts and suspenders approach of the interior drywall, the thermal barrier actually inside the cavities, and then our exterior sheathing, for example, here. So an example of this is when you go into a house and you see an assembly like this, you don't necessarily you're not necessarily able to quickly understand where the interior and exterior air barriers are, what's going to be insulated, what's not going to be insulated, and how you're ultimately going to get continuity. So if we take another example, we can kind of walk through it. Now, just to orient you to this picture, we're standing on a bridgeway. Over the railing would be the great room of the house. In all that framing back behind there is the attic space above a bedroom, probably the primary suite there. And we see a duct that's in the assembly there. And so the first question we might want to ask to be able to define the building thermal envelope is, do we want that duct to be inside or outside the building thermal envelope? And you could type in an answer to that question in the chat so that we get a little bit of understanding of what you're thinking there. But I'm going to move on pretty quickly here and tell you that we want that duct to be inside the building envelope. And in order to do that, we're going to insulate this wall. We're going to insulate behind the duct, and we're going to insulate down the wall of this loft area here as well. And then maybe we're going to sheathe the attic side of that assembly to bring that insulation to help create that boundary between conditioned space and unconditioned space. And we're going to drywall on the inside, and the drywall is going to come around this duct chase and go down the loft wall here. And we've got kind of enclosure of the insulation there. So I'm going to ask you real quick, is that duct inside or outside the building envelope as I explained it? And again, you can type an answer in the chat if you want to. But again, moving forward, I would tell you that the duct is not inside the conditioned space yet because we have misalignment of the continuity of our air barrier and our thermal control layers in this house. If I don't get a supplemental air barrier in this chase adjacent to the insulation that's going to be in that chase, the drywall that comes around the duct chase here just becomes aesthetic. It's not doing its suspenders or belt portion of its work there. It's changing over to just be an aesthetic detail there. And that's why we have to add that supplemental air barrier to get that enclosure of the insulation, to make sure that we have an assembly that actually works to give us control and predictability of airflow, thermal flow, and moisture flow in our assemblies there. So you'll see that the code goes further and it defines the continuity of the air barrier system, and it defines the air barrier itself as an assembly of things that are coming together to prevent the passage of air through the building thermal envelope. So we have all of these different assemblies. We have air barrier assemblies. We have thermal control layers, assemblies that are coming together to create that assembly there. And in its simplest form, again, we have the interior drywall and the continuity of the interior drywall. We have the exterior sheathing and the continuity of the exterior sheathing. And we might add additional layers like house wraps or other water control layers that also can help us from a thermal and air perspective as well. But really that house wrap is its primary purpose is a drainage plane on the exterior there. And then when we think about the function of this, we need to understand that we're trying to enclose insulation, especially fibrous air permeable insulation in six-sided enclosed cavities there. We're trying to get better air control, thermal control, and moisture control in those assemblies. So now that we have a kind of an understanding of the building thermal envelope and how we want to insulate and create an airtight assembly there, let's think a little bit about how energy moves through insulation and kind of the thermal flow or thermal control that we're trying to gain here. So the first thing that we need to understand is that heat is the transfer of energy between physical objects. And it's always moving from higher concentrations to lower concentrations, or you can think of it as from hot to cold or more to less. It always will move in that direction. So when we have clearly defined our building thermal envelope, we've also created what we call a delta T location in our heating seasons and our cooling seasons so that we know which direction the energy is moving. Is it moving from inside the house to outside the house in the wintertime, or outside the house to inside the house in the summertime? And we know how we can control that and get better predictability of that heat loss and heat gain by the building thermal envelope that we're going to build. But how does that energy actually move from inside to outside or outside to inside? It moves by these three primary means of energy transfer: convection, radiation, and conduction here. So we're going to start out with kind of a little deep dive on conduction. Conduction is energy that conducts through a solid objects, always again from warm to cold until a balance is reached. And when we look at it from our house perspective, again, if we have the exterior temperature at 20 degrees and the interior temperature at 72 degrees, we know that the energy is going to go from higher concentrations to lower concentrations. So it's going from inside the house to outside the house. And we are creating a building assembly that's going to resist the flow of that energy. Now it's going to resist the flow more inside the cavity than it is at the framing members there, because the R value of wood is only about 1 per inch, and the R value of our assemblies can be as high as 23 or greater, depending on the type of insulation that we're going to use there. But the whole objective of the insulation is to resist the flow of energy from higher concentrations to lower concentrations, and for its ability to conduct through that assembly, that building thermal envelope assembly that we just described before here. And, why does it matter? Is that we often get assemblies that aren't built properly or assembled properly in order to get that full resistance of the insulation of the building thermal envelope to give us that control and predictability of thermal flow by conduction from higher concentrations to lower concentrations. We also see that there are other types of assemblies that can create large conduction points or thermal bypasses that we talk about here. And in this case, we have the figure 1 here, that's showing an improperly insulated slab edge. And we're not only going to get comfort issues in that house, but we're going to have excessive heat loss or heat gain through that misapplied insulation there. That's not creating a thermal break between the slab edge and the conditioned space of the house there. So again, creating that clear boundary condition between conditioned space and unconditioned space. And just, quickly here, there is a section of the code that talks specifically about slab edge insulation, that it needs to extend downward from the top of the slab. It needs to extend 2 to 4 feet, depending on your climate zone. It doesn't mean that it has to be all horizontal. It can be vertical extension as well. And that you can cut that insulation at a 45-degree angle there. But the code does give us installation instructions, as well as manufacturers who are manufacturing the insulation, their instructions. And we basically are required to follow both manufacturer instructions and code instructions with regards to installation. Now, the other way that energy moves from inside to outside our houses is energy that's moving with air. It's energy that's transferred by a fluid, and that fluid, it can be air, it could be water as well, but from a house perspective, it's generally we're talking about energy that's moving with air, and that energy that's moving with air can cause the insulated cavity to malfunction or not work as well or as it was intended. And in this case, we've got what's called a convective loop happening inside of the building cavity, because we have gaps, voids, and compression in the insulation that's been installed in the cavity. So the air inside that cavity is going to warm on the interior side, where the temperature is at 72 degrees, and it's going to rise inside of that cavity. And as it hits the top plate, it basically gets moved over or kicked over to the exterior of that envelope, and it begins to cool. And in that cycle of heating and cooling creates a convective loop that is actually able to transfer energy more quickly from inside the house to outside the house, versus an assembly that was insulated properly, that fully filled the cavity full of insulation and whatnot, so that we could avoid the convective loop, and we would go back to conduction, which is a slower movement of energy from that higher concentration to the lower concentration. Now, convective loops happen inside of our houses as well. Convection is described by a pathway that we often talk about in building science, called stack effect, which just describes what happens to air as it warms. Air rises as it warms, and as it rises, it can create a convective movement of energy around, because it's going to rise and hit maybe the ceiling of our house and then get moved over to the side walls and start losing some energy and cooling and whatnot. So we can have these convective loops inside of our houses. We can have these convective loops inside poorly insulated cavities. And so one of the big things that we need to look at from a code perspective is how well the insulation has actually been installed in the cavities. And this is one reason why we're starting to see more and more blown products be installed versus batt insulation in our cavities, is because you're going to get truer R value in the assembly, and you're going to get a better performing assembly there. And just an example of the ineffectiveness of poorly installed insulation can be described here. So we've got a box, we've created a heat source in that box and taken a thermal insulation or a thermal image of the 4 insulated bays here. So my question to you is, which bay do you think is performing best? So keep an eye on the cavity that you think is performing best here. So we have cavities that range from no insulation to an R19. And the big reveal is going to come here real quick. So quickly make a note of which cavity you think is performing best here and which R value corresponds to that cavity. And you might or might not be surprised here. But if we look at cavity 1 here, that was insulated with an R11 batt, and it was insulated according to manufacturer instructions, or what the ResNet standard says is grade 1 installation, which is equivalent to how the code is requiring insulation to be installed there. Cavity 2 is R19, and you can see that there's a large gap or void at the top of that cavity there, where heat loss is being accentuated instead of being resisted by the R value. So conduction is happening much faster at the top of cavity 2, even though it has more R value than cavity 1 there. Cavity 3 is R13. It's a decent install, but the insulation is probably cut a little short at the top there, and there's some gaps and voids there. And then cavity 4 is our non-insulated cavity there. So you might be surprised that, you can have better performance with less R value if that insulation is installed properly there. And obviously we want the combination of higher R value and best installation in order to have the cavities that meet the requirements of the current energy code that you might be working in there. Now, from another perspective of how energy can move in and out of our houses is with radiant energy. And this is energy that moves from objects of higher temperature to objects of lower temperature. So the best example is from the sun to the earth. It's literally moving through space from a super hot object to a super cold object. We get an example of that in maybe the summertime when we go camping and have a fire. We feel that radiant energy from the fire on the front side of our bodies, but we don't feel it on the back side of our bodies if we're facing that fire there, because radiant energy moves in a linear pathway. And how we see it most often in houses is with regards to windows. Basically, our body heat is radiating to that window and then conducting through the glass to the outside. But it is another pathway of energy loss in our houses there. And the ones that affect insulation the most, however, are conduction and convection there. And what we use to resist that flow from a conductive perspective is R values, and the R value of the insulation. It's the capacity of an insulation material to resist heat flow, and R stands for the resistance of heat flow, and the greater the R value, the greater the resistance of heat flow. Now, the other side of the equation is how well the insulation is installed. And IECC says that we need to install according to manufactured instructions. But again, we're going to see some examples of where the code is adding to manufactured instructions. So we also need to think about the requirements that are in the code. And I don't know how many of you have actually read the manufactured instructions for how to install a fiberglass batt. I would say few of us actually have, but basically it says that we need to fill the cavities from top to bottom, from side to side, and front to back. and we should have limited to no, actually the instructions generally say we should have no gaps, voids, or compression inside that cavity when you're talking about the installation of a fiberglass bat. And why do we want that? Well, it's because insulation in our homes works exactly the same way that insulation on our bodies work. So this person has a fleece jacket, and the objective of the fleece jacket is to trap a pocket of air. And it really doesn't matter if it's a fleece jacket or a wool sweater or a down parka or a cotton sweatshirt. The objective of those insulation materials against our body is to trap a pocket of air. So, with that said, we understand that it's the pocket of air that is resisting the heat flow from higher concentrations to lower concentration, not the material. The objective of the material is to trap that pocket of air, and the pocket of air, it's what's giving us that R value there. And so ultimately, what we're looking for is a stagnant pocket of air, a pocket of air that doesn't move around in and out of the insulation, that just remains in one place to give us that resistance to the flow of energy. So when this person walks out on a windy day outside, we see that the pockets of air can't remain stagnant anymore. They're going to be flowing in and out of the fleece jacket here, and we're going to be cold when we go out on a cold winter day. So what do? We put a nylon shell over our thermal barrier. So we have an air barrier or an air control layer over a thermal control layer in order to get a system that works, in order to stop the movement of air from taking energy out of our insulation, and in order to get that stagnant pocket of air in our assembly there. So in reality, we have a system that works, and in reality, it mirrors what's happening in our assemblies of our home as well. So we have all of these components that are coming together, these different pieces of the assembly that are coming together. And the insulation itself resists conduction, but it doesn't resist the flow of air through it, especially if it's an air permeable insulation, which the majority of the insulations that we use are. Therefore, we have to have that building thermal envelope that is defined by the continuity of our air barrier system and our thermal barrier system all the way around the house in order to have an assembly that works and works well to resist the flow of energy from inside to outside, from outside to inside. So the biggest myth that we have about insulation is that it stops the flow of air. And we need to realize that it doesn't stop the flow of air. And this is really all with regards to air permeable insulation. There is another type of insulation out there that's called air impermeable insulation. And air impermeable insulation is defined in the IRC as insulation having an air permeance equal to or less than 0.02 liters per second. They're at a specific pressure there. And it can be tested per specific standards and whatnot. And what we're talking about, air permeable insulation, in most cases, we're talking about foam type products. We're talking about closed cell foams or open cell foam. So the picture on the left is an open cell foam, and the picture on the right is a closed cell foam. And the big difference between the two is that the closed cell foam remains or creates a chamber where a stagnant pocket of air is maintained inside of that chamber. With open cell foam, you can see that the chamber is broken apart more, and it traps a pocket of air, but it doesn't do it to the same degree as the closed cell foam. And that's why an open cell foam has a lower R value per inch than a closed cell foam. Why its density is less. So closed cell foam is soft to the touch, and a closed cell foam is hard to a touch. It also is not as good an air barrier as a closed cell foam because the structure of the cells inside the foam aren't the same there, and you need to have more more quantity, more depth of the material to be classified as a true air barrier as well. The other thing that we need to think about is the moisture barriers here, or moisture retarders here. And closed cell foam can be considered a class 2 vapor retarder at about 2 inches of material. It's a 1 perm is a class 2 vapor retarder there. And we'll go into vapor retarders in much more depth on another presentation, but we need to understand that vapor retarders and air barriers, or air barriers and vapor barriers, they are not the same thing. They're achieving different characteristics and performing different functions, but there are some materials that can be an air barrier and a vapor retarder in the same product there. When we go down even further, we need to talk about U factors and R values. So we've already kind of described R values. U factors are the reciprocal of R values. So if, in this case, if you take 1/5 R, you get a U factor of 0.20, which is not an uncommon U factor for a window, for example. But the big difference between U factors and R values is that U factors describe the assembly of things that are creating the resistance to the flow of energy. And the R factor applies to a construction component, like the insulation that's going into the cavity there. So the cavity itself would be described by the U factors of our interior drywall to our exterior sheathing and everything that's going into that assembly to create the resistance to the flow of conduction from inside to outside or outside to inside. And the R value is just describing one component. And that's really one of the big reasons why we always use U factors to describe windows, because we're not describing the center of glass R value. We're describing the entire assembly of that window's ability to resist conduction from, again, inside to outside or outside to inside, from higher concentrations to lower concentrations there. So we do have a U value table in our energy codes here, but the reality is that the U value table or U factor table is describing the assembly of our wood framed wall, in this case, in climate zone 5, but its primary purpose is for the utilization of energy modeling softwares there. That's really why we want to know the U factor of the assembly, is that we need the U factor to be able to do an area weighted U value trade-off when we use a ResCheck software or a energy gauge or Ecotrope software, REMrate software. All those different softwares can do that type of analysis. But when we do that analysis, we need the U factor versus the R value. So the R value table is what builders and code officials tend to concentrate on more than the U factor table. Now, the R factor table is telling us in climate zone 5 what the wood framed wall needs to be, or what, in whatever climate zone, what the what the R value of that wall needs to be there. And what you'll see here is that now we're given a lot of choice in how we can insulate that wall if you're utilizing the prescriptive R value approach for code compliance here. But we're also seeing that the R values have increased, and that the R values are starting to shift to more concentration on putting some R value on the exterior of our homes here. So before we get into that, I just want to do a quick demonstration of how the R values and the U factors correlate with each other. Basically, they're describing the same thing. One is describing it from an assembly perspective, and one is describing it from a component perspective. So if we look at climate zone 5 here, and the U factor is at 0.045 requirement for the assembly, if we take the reciprocal of that, we get R22.2. And so the R value requirement in the table is R20 plus 5. And if we look at that and we take the reciprocal of that, we get 0.04. And what we know is that the difference in the 5/100ths of a U factor is that those assembly details there. So the components that the R value table are looking at are the cavity insulation and the continuous insulation, but the U factor table is looking at the air film on the inside, the drywall, the studs, the assembly R value, the exterior sheathing, the exterior weather resistant barrier, the siding that's on that house, and any air film that's trapped in there as well. So that's what constitutes that 0.005 difference in the between the U factor table and the R value table there. So it's a little complicated, but I just wanted to give you an idea that the U factor table and the R value table are really doing the same thing. What really matters more than that is the installation of the material. How are we going to install it to get an assembly that actually works as described by our building thermal envelope? Now, I made a quick reference earlier about ResNet and ResNet's grading system. So some of you might have heard of grade 1 installation, grade 2 and grade 3 installation. In that system, grade 1 is the only grade that's equivalent to manufactured instructions and the requirements of the code. But ResNet is in the process currently to redefine their insulation assessment for their software compliance and development of an energy rating index score, specifically the ResNet Energy Rating Index score there. And they're moving to a properly installed versus not properly installed evaluation of the insulation installed for a variety of reasons, but one of the bigger reasons is that it's in better alignment with the way that the code looks at the requirements for installation of insulation. The code basically, and manufacturers basically, are not able to tell you to install insulation kind of right or with a little bit of defect. They basically have to tell you to install the insulation perfectly, or in the requirement from a manufacturer, it is to say no gaps, no voids, no compression there. They can't tell you to install it with a little bit of compression. So the ResNet grading is going to move in that direction. And what they're ultimately going to do is break down these different insulation materials and tell you how do you look at that, how do you assess it, to demonstrate that it's been installed properly so that it can be modeled, energy modeled with its rated R value. And if it's properly installed, it can be rated and modeled with its properly installed R value, which means that it's been installed according to the code. So, and ultimately, we're going to get better alignment between the energy rating index, energy modeling, and the code requirements for modeling there. Now, another example of why the installation of insulation is so important is if we take the simple example of an R19 bat in a 5.5-inch cavity that we call 2x6. So a nominal 2x6 wall, the cavity thickness is actually 5.5. An R19 bat is 6.25 inches thick. In order to install it properly in the cavity, we have to compress it by 3/4 of an inch there. And if we take that compression into account, we actually see that its R value is decreased because it can no longer trap the same quantity of air in that 6.5-inch or 6.25-inch insulation there. So whatever we know, however, we know that R19 in a 5.5-inch cavity, if it's installed perfectly, actually is about 17.8 R value. And we generally round it up to R18. And this is proven time and time again by manufacturers in their compression charts. They have these charts, they publish these charts, and you can see that an R19 bat in a 2x6 cavity is actually a R19. And that's why they've come out with R20 and R21 and even an R22 bat that actually fits a 5.5-inch cavity and would get its rated R value if installed properly. But that means that when we go out and inspect for the insulation install, that we need to be looking more than just is the insulation in the cavity. I can't look at this and say, yep, I see pink in the cavity. I'm going to go on to my next job and look at it there. I need to actually ask myself two questions. Is the insulation there? Yep. Now I need to look at it more closely. Has it been installed so it will work? Is it there and does it work? Become a crucial part of our inspection process when we're looking at insulation. Is the insulation there? Yep. But when I look at how it's been installed more closely, it's not installed so it will actually function and work. So I should fail this inspection of the insulation because they haven't split the bat around the wiring. There's excessive gaps and voids and compression in the insulation. So we're not going to get the rated R value of the material that's installed there. Now, some of this inspection should be obviously done after installation, but should be on the shoulders of the installer as well here. And that's what this section of the code is getting at in Chapter 3. It says the building thermal envelope insulation, if it doesn't have an R value mark, the installer shall provide a certificate listing the type, manufacturer, and R value of the insulation. And then it goes on in another section, the R303.1.2 section, to say that for installation materials that don't have that R value mark on it, the installer has to leave a insulation certificate to certify the R value of the material that's been installed immediately after the installation of that insulation in the cavity there. The reason is that we have so many materials here that we have no idea what the R value is. And the R value is so dependent on its installed density or how the insulation has been installed in the cavity there that we as inspectors can't go in there and determine what the R value is. Therefore, the installer should be verifying and doing some level of quality assurance to verify what the R value of that material is and leave a certificate that can be inspected at the time of install so that when we go out there after install, we can determine did they achieve the R value that's required in that particular assembly. If we're using the prescriptive approach, it's got to be like 20 plus 5 or an R30 cavity without anything on the outside. If they're using a performance compliance approach, well, they might be able to trade off and just have an R. I mean, potentially they could have an R19 in that cavity. But if they did put an R19 bat in that cavity, remember, it's not performing like an R19 bat, even if it's installed properly there. So they should be modeling it as an R18 in that cavity there. So there are techniques to evaluate the R value of the install of blown materials. You see on the right there are two gauges that are on the market that can measure the R value of installed material based off of the density of the blow and the amount of air that can move through that material. Or you can simply cut out a square foot of material and measure it and get its density that way as well. Now, the certificate on the left here is not the certificate that the insulator would be leaving behind. They need to leave behind a much more in-depth material. This certificate is telling us that at R38, this particular material needs to have 10.5 inches of material to get that level of R value there. And why we bring that up is that there are some materials that need like the one up above, needs 14.5 inches of material to get an R38. So it's very dependent on the installation and understanding what material you're looking at. And, just because it's fiberglass, it doesn't mean that it needs 14.5 inches. There are different brands of fiberglass that might need up to 17 inches of material to achieve an R38 there. So again, another reason why we really need to begin to rely on and ensure that we get the certification of the installer at the time of installation, that they're certifying their install. They're taking responsibility for that R value that's been installed in those cavities there. Okay, so next we need to look at some of the instructions for the installation of insulation. A lot of those instructions happen through the manufactured instructions, as I showed before, but a lot of those instructions happen in this table here, where we have the general component down the left side of this column of this table, the air barrier requirements, and for all the air permeable materials, the air barrier requirements are crucial there, not only for the air tightness of the house and the convective losses of energy from poor air tightness in our homes, but also to keep that stagnant pocket of air stable in it. And then we have insulation instructions that go beyond manufactured instructions here. So if we look at this more closely, we look at the general criteria here, we can see that they're calling for the continuity of our air barrier systems, that the building thermal envelope needs to be airtight and all breaks and joints need to be sealed. But we also see that air permeable insulation shall not be used as an air sealing material here. So we're talking about using foams and caulks and whatnot, but we see time and time again materials like this being used as air sealing materials here. And we see often that the materials that the installers don't necessarily understand what their materials can do and can't do. So this is an example of a fiberglass bat being installed so that it's blocking a hole basically from inside to outside. And they think that if they put some foam around that hole, that it's going to stop the movement of air. So we need to understand what our materials can do and can't do and help educate our trade partners that we don't need foam here. We actually need an air barrier here, maybe supplemental thermoply or foam board or drywall or something there that's going to actually stop the movement of air and allow that insulation to trap at the pockets of air that are needed there. And you just, again, see it time and time again here. Now, this section of the code basically says that we at our rim joist, the insulation doesn't have to be enclosed on all sides with an air barrier system, which means that the rim joist itself needs to be a rock solid air barrier. The code asks us to put a detail in our construction documents to help detail that. And we see here that are required to seal the rim board to the subfloor, the rim board to the sill plate, and the sill plate to the foundation in order to get the continuity of our air barrier system and ensure that this assembly is going to be airtight. And then we're going to install the insulation against that so it's in permanent contact with the air barrier system. And we have the continuity of both our air barrier and our thermal barrier all the way around the house here. Now, that's great in theory, and it's much easier to get the air barrier portion of that assembly working than the thermal barrier of that assembly working because of the way that we often insulate our rim joists. And you can see here in the center picture, this kind of crescent-shaped bat here. It means that the bat is not in contact with the rim joist or the rim board of that assembly. And all of these puffed out insulations are examples of insulation that has not been installed well. And that's why one of the things we're starting to see is more and more foam products being installed in those assemblies there. Whenever you see a crescent-shaped bat, you should be wary that the bat is not installed properly there. It needs to be in full contact with the surface that it's intended to insulate there. And here's just some more examples of poorly installed batt insulation. Another example of where the installation instruction might show up here is in the specific insulation section, the R402 section of the IECC, in this case, ceilings with attic spaces. It's telling us prescriptively that we can reduce the R value of our attic insulation as long as it extends over the wall top plate at the eave. So the requirement for the installation, regardless of the R value, is that the insulation needs to extend over the top plate and it can't be compressed over the top plate. It has to be installed at the depth of material to achieve whatever R value you have proposed to put in that piece of the assembly there. Because prescriptively, yeah, it says I can go from an R60 attic in climate zone 5 to an R49, but I might use a performance compliance approach that I'm proposing to put R30 out there, or maybe R19 out there, or whatever it is. So there are two requirements here. One is that it fully covers the top plate, and the other requirement is that we have enough heel height in order to receive the insulation at whatever required R value there. So we really should be looking at energy heels on all our plan reviews to ensure that we have the proper amount of insulation over the top plate that whoever the builder proposed to put in that particular location. And if we go back a few slides, you'll remember that R38 took somewhere between 10.5 inches and 14.5 inches in the two examples that I gave to achieve that depth over the top plate there. So you're going to need a pretty substantial raised heel truss in order to do that. Also, if you're going to put in attic eave baffles for a ventilated attic, which you'll need some space for that as well. So you might need a 10 to 15 inch heel truss in order to get that. And with an R49 there, you're going to need an even, potentially more substantial there. Now I bring this up as well because the attic eave baffle is crucial in the performance of an air permeable insulation in an attic. And we're trying to ensure that the ventilation air doesn't drop into the attic insulation, doesn't cut into it and affect those stagnant pockets of air that the insulation is trying to trap. And so the new requirement in the 2021 IECC is that we have continuous baffles. If you're going to just spot soffit vent the assembly, you still have to put continuous baffles in there to ensure that there's no bypass of the ventilation air in that assembly there. So our ultimate objective here is that we stop wind washing and wind intrusion in the insulation, that we move that air up and over the ventilation air up and over the insulation. And if the ventilation air is going to drop into the insulation, it's going to drop into the top quarter of the insulation and not get all the way down to the drywall level that's separating conditioned space from the ventilated attic. And we continue to maintain that stagnant pocket of air there. With another kind of interesting thing with roof assemblies is that you have to make a choice if you're raftering that roof assembly. Is it going to be a vented or unvented assembly there? Because the ventilation air is not smart enough to travel the black line that's depicted here. It's just going to roll itself through the insulation and degrade the R value of any air permeable insulation unless we clearly define a ventilation space that's separated from the insulation space here. So again, we should add these type of details on our construction documents here, and we need to create assemblies that actually work there. Otherwise, you're going to be moving to potentially an air impermeable material and building a roof assembly as defined in the IRC in section R806.5 for unvented attics. for example, and it goes through all the things that you need to do in order to achieve an assembly that works with air impermeable insulation and when you're not going to be ventilating that assembly itself there, which means that you need to pay particular attention to the next session that's going to be talking about vapor retarders and understand the difference between vapor retarders and air barriers here. And unfortunately, we just don't have enough time to go into that in any depth, except to say that a lot more moisture moves with air than it does by vapor diffusion. And therefore, we need to really concentrate on those air barriers, not only from the perspective of maintaining that stagnant pocket of air and the integrity of our building thermal control layer, but also from a vapor control perspective as well here. The other reason we bring that up is that thermal bridging is a big component of the insulation that's installed in our assemblies there. And when we have excessive building thermal bridging and we have excessive moisture buildup in our assemblies because we're not building a tight enough assembly there, we have the possibility of moisture that's in that assembly to condense on the first condensing surface on the outside here. So this is what's called a cyclometric chart that shows us if I have relative humidity at 35% and the air temperature is at 70%, if I hit a surface that's at 40 degrees, we're going to get condensation in that assembly there. And the surface temperature of our exterior sheathing is often at 40 degrees here. So we have gained control and predictability by building our assembly tight and getting control of convection and conduction there. But sometimes if we don't have control of the air leakage in our assemblies, we can get moisture build up in that assembly there, and we're going to get excessive condensation there. So this is the primary reason why we're seeing the code starting to move insulation outbound to the exterior, because just like putting a foam koozie on our cold can of soda here, if I warm the exterior surface, I'm going to get less condensation, less repeated wetting of the assemblies there, and I can ensure that I'm not going to build an assembly that has a vapor retarder on the inside that doesn't allow moisture to dry to the inside of our assemblies. So again, pay special attention to the vapor retarder section that's going to be talked about in one of our upcoming sessions here. I'm going to skip this basement wall part here and just go to this class 3 vapor retarder section, which is really our last slide here. So you can see if I move the insulation outbound and I get an R value to the exterior of my assembly, I reduce the thermal bridging that I was talking about, but I also give myself the ability to use a class 3 vapor retarder, which is a more forgiving assembly that allows for drying potential to the outside. So I've reduced the potential for condensation in the cavity, but I know that maybe some moisture might diffuse through a class 3 vapor retarder. I give that moisture the ability to dry back out seasonally in that assembly, and I have a more robust, more resilient, better insulated, better protected assembly from moisture perspective as well. And I get a holistic assembly that's going to perform for me over time, which is ultimately what I want here. So to conclude, we understand that insulation's job is to trap a stagnant pocket of air and keep that pocket of air stagnant to resist conduction. And the resistance is measured by R value here. We see that inspection is important, that we want to avoid gaps, voids, and compressions in the assembly. And we need to ask the question, is it there and does it work as it's been installed? we need to begin to rely more and more on the insulation certificate that should be left immediately after the installation of insulation so that we can determine has the R value been achieved, especially in R value products that aren't labeled as they don't have an R value mark on them. Insulation R values are talking about the components that build our building thermal envelope assemblies. The U values talk about the U value of the entire assembly. The U values are primarily used for energy modeling. The R values are obviously used as a compliance approach using the R value table when we're talking about complying with the IECC. And then insulation is moving outbound to give us more resilient assemblies that are less susceptible to moisture condensation, mold growth, and deterioration of our assemblies there. And you can see in the picture on the right here that it's all about how well the insulation is installed and getting the integrity of that insulation and maintaining a consistent R value is achieved often by getting that insulation to the exterior of the building envelope there. Most of the rigid insulations are less susceptible to gaps, voids, and compression. That's not going to happen. So we're going to get a truer R value. We're going to get a better performing house from a comfort perspective, from an energy efficiency perspective as well. So thanks so much for joining us today. Happy to stay on and do some questions. If some people have to leave, have a great day. But if you need to contact me, here's my contact info.
Awesome. Thank you so much, Robbie. Always a great presentation from you. So we will open it up to questions. We got a couple that came in. First one is just, Robbie, would you mind sharing the PDF of the slides with me so that I can get that posted with the recording to the Code Adoption Toolkit?
Yes, for sure.
Perfect. Okay, the other question that we got, and anyone else feel free to chime in at the Q&A or the chat function, and we'll go ahead and answer your questions there as well. But we had a question about, are there prospects for a standard building energy efficiency certification that mirrors the energy passport from the European Union? This would be an MPG sticker that allows apples to apples energy comparisons between buildings. I said that I'm not aware of it, but wondering if you are.
Basically, the ResNet HERS Energy Rating Index is a very similar thing.
Perfect. Thank you. All right. Well, Robbie and I will stay on the line for another minute here. If there's any other questions that come in, that's great. If not, we hope to see you on the 24th for the next session on vapor management.
Yeah, make sure you come to that because it folds in like a glove to all the insulation stuff that we talked about.
Great. I'm not seeing any other questions here.